Octal and hexadecimal numbers are very important in a binary system. Even though they're not binary numbers, they're much easier to read than binary numbers, and it's easy to convert from octal or hexadecimal to binary and back from binary to octal or hexadecimal because they're both powers of 2. 2 to the 3 is equal to 8, and 2 to the 4 is equal to 16. So we might want to practice that conversion. So if we have a decimal number, and again, we can convert from decimal, but it's a little bit more difficult to convert from decimal to binary, especially once the numbers get larger. But to convert from decimal to hex or octal is really quite, is much easier. So for our hexadecimal system, that means we have 16 distinct digits, and the first 9, or the first 10 are the same, 0, 2, 3, 4, 5, 6, 7, 8, and 9, but we need, for in terms of digits, we get 16 here, so our decimal 10 becomes, then we just count A, B, or C, D, E, oops, did I do something wrong? E, F, no, I didn't do anything wrong. And then lastly, our 16, that's our 1, 0, where we go to 2 digits. For octal, we can only go through 7, right? 0 through 7 are our octal digits, and we get to 8, that's our 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and then a 16 is a 2, 0. In binary, converting to binary, we want to be able to do this quickly as well, because this is where, particularly in lab, we'll be using these switches. So it's just a 0, but for 4 digits, it's 4 zeros. And then our least significant digit will toggle every time, and our second least significant digit will toggle every other time. So we have 0, 1, 2, 3, we get to a 4, and then 0, 4, 5. Then we're going to toggle our second digit again, and then we'll leave that the same, and then we get to 7. So we want to be able to recognize these. Once we get to 8, this fourth bit goes on, and then our third most significant digit toggles every fourth time. So we can go down that way if we want as well, and just keep toggling this one every time, because it will, and toggle this every other time, and then this one every fourth time. And then we're going to have 8 zeros, so I have 1, 2, 3, 4, 5, 6, 7, 8 ones. And then of course our 16, that's when we have the fifth digit. All right, so we want to be able to do that quickly. I mean, you could look it up in a table, but you want to be able to do that quickly and be able to check it and get used to it. So again, our octal and hexadecimal numbers, each octal digit corresponds to 3 binary digits. Our 2 to the power of 3 is equal to 8. So if we have this binary number, we can convert that quickly to base 8, or to an octal number, if we separate by 3. So we have to recognize where is that decimal point, and we have to take 3 in this direction, and then we have to take 3 to the right of the decimal point, 3 to the left of the decimal point. So when we go off in this direction, we have to start from next to the decimal point. And we go off in this direction, start to the next to the decimal point. So really what we need here is a 0. We can represent all 3 octal digits. If, for example, we just had 0, 1, 1, 0.1, that would be our 3.1. That we would convert that to in decimal, we convert that to 3 1/2, or 3.5. So in octal, this becomes a 3.4, right? So it's our 3 plus 4/8. excuse me, yeah, yeah, that's correct. So that's pretty easy to do. We can just separate them. If we're converting it to hexadecimal, then we use 4 binary digits. So if we, again, we go off to the right of the decimal point, separating by 4, go off to the left of the decimal point, separating by 4. And then we do our conversions. We just need to know um, to know how to convert for 4 bits binary to hexadecimal, or for 3 bits binary to octal. So that these were separated nicely. If we look at this example here, we just have a string of digits or a string of bits. And if you get enough ones here, it's hard to count how many that you actually have. It's hard to actually see that. So there's no decimal point here. But you know, so we don't see a decimal point. We put the decimal point to the right. We assume that's where it is, or the radix point. So when we're converting them, it's easiest just to block it off so that you can see it. But when you're writing out a string of binary digits or binary bits, it's nice to separate them. You know, if we have a very long, you know, if we have 1,132,411, right? We put our commas in there. So what we can do is a space. You can space every 3 or space every 4. Typically now we space every 4 because we're more apt to use hexadecimal conversion because we have so many bits. The density of memory now is so large. So this would then convert to 7 in octal, 7, 4. This would be a 3. This would be a 5. Whoops, that's a 5. And then we'll have a 1 here. If we're doing every 4, there we go. I guess we get even number there. So this is still a 7 because that's a 0. But here we have this is 8, 9, 10, 9, 10, 11, 12, 13. So our 13 is a hexadecimal D, which, you know, you should check that. But and then our 1010, that's a decimal 10, that's a hexadecimal A, and a 100, this is our 12. This is 12. This is 13. So this is the D. And what do we have here? This is a 14. So this is an E. So we'll put our E here. All right. So you can check that. In fact, that is exactly correct. So this is how we can easily convert back and forth between hexadecimal, octal, and binary. Again, all because they're all base 2. If we want to do multiplication, we have multiplication tables that we've memorized in base 10. We can also use multiplication tables for octal and hexadecimal. So we'll show an example of doing hex multiplication using a hex multiplication table in the next video.